Good morning, everyone. I'm Aadesh Madnaik, and I'll be presenting Renting Edge Computing Resources for Service Hosting. This work was authored by Aadesh Madnaik, Professor Sharayu Moharir, and Professor Nikhil Karamchandani. We work with the following context. We see the deployment of several cloud computing architectures. Usually, they can be classified into one of the following: software as a service, infrastructure as a service, or platform as a service. Each of the applications like search engines, video on demand services, or navigation services require the deployment of one of these architectures. In addition, mission critical applications require cloud computing services, mainly due to the advantages of stringent privacy requirements and managing high data traffic loads. This paradigm necessitates the deployment of storage and computation closer to the end users, which causes us to introduce edge computing as an architecture. A typical edge computing architecture looks like this. We have three separate entities: mobile devices, the edge servers, and the cloud servers or the backend servers. The mobile users are closer in proximity to the edge servers. The edge servers and the backend servers are connected through an IP core network. The edge servers can manifest in several different forms. They can either be adapted from cellular base stations or shopping centers or parklands, etc. The edge servers can serve multiple users and they can host requests from or host services from several different cloud servers. The edge computing platforms advantage from the following. They have low latencies because of closer proximity. There is also decentralization of computation, and each of the edge servers can host services from multiple backend servers. However, this comes at a cost. Edge servers usually are limited in their computational capabilities, and switching the hosted service is very expensive, both in terms of time and computation load. Through our work, we propose a deterministic online policy called Better Late Than Never. We analyze the performance for stochastic and adversarial arrival processes, and we compare our policy with optimal and other established policies. We also provide fundamental limits on the performance. This is the problem setup we work with. We have an edge server, we have a backend server. The edge server can be hosted in one of two states, a high state or a low state. And the state is controlled using policies better late than never or follow the perturb leader, for instance. The edge server has to serve the requests determined through a stochastic arrival sequence. Each of the requests that the edge server cannot serve are forwarded to the backend server. There are costs incurred with each of the following steps. Without loss of generality, we consider kappa h greater than kappa l. We discuss the performance of policy P under the following costs. Each of the requests forwarded to the backend server is served at the cost of 1 unit. This is known as the service cost. Switching the state of the edge server from a high state to a low state or vice versa is known as the switch cost. Hosting the edge server in a high state incurs a rent cost of CH, and hosting the edge server in a state L incurs a cost of CL. Our task is to determine the optimal state decision sequence, RT, and RT is either one of H or L. The total cost in a particular time slot is modeled as the following. Each of the requests forwarded to the backend server is a service cost. Switch costs are determined based on the past state decision sequence, and rent cost is dependent on the current state decision sequence. We work with better late than never. This is an online policy, which means that it does not have the knowledge of future arrivals. The policy is modeled as follows. We consider the current time slot to be t, and we consider t switch to be the last time the server had changed state under the BLTN policy. The algorithm looks as follows. We iterate over tau bounded between t switch and t. For each of these time instances tau, we evaluate the total cost to switch in time slot tau rather than at the end with t. If the total cost is lower, we decide to make the switch. Analytically, this is what BLTN looks like. We define capital W to be the sum of switch costs, switching from state H to L and L to H. We define HT and LT to be costs to remain in states SH or SL. Now, we consider a scenario where the state in time slot T is SH. Now, we decide to change state from SH to SL if the algorithm can find a time tau such that the following is true. The time to remain in state H till tau plus the cost to stay in state L from tau to T should be less than the total cost incurred in staying in state H all the way from T switch to T. All in all, this simplifies to the following expression. If BLTN policy can identify a tau such that this is true, this state switch is made. Similarly, we can consider the reverse case where we start off in a low state and we decide to switch whether to switch to a high state. If the total cost of staying in the low state plus the high state after a certain point tau is less than the cost incurred in staying in just the low state for all of the time duration, we decide to switch the state. We observe that the time complexity of BLTN usually is the order of T. It's a very high order time complexity because this comparison needs to be made for a range of tau. However, for a range of tau, However, through dynamic programming, we can reduce the order to order 1. This calls for the introduction of a new variable, delta t. We define it to be as follows, and we evaluate delta t for each time instant t. After one comparison, we can make a decision. It's equivalent to evaluating this analytical expression. A similar delta t variable can be defined for transitions from H to L. I'll illustrate this through an example. Uh, Consider delta t to be the following. We start off in state L. We consider these numbers as the parameters that we are dealing with, and we model the request arrival sequence as follows. Now we have to calculate delta t for each interval from 1 all the way to 11, and this happens in succession. So delta 1 is calculated by inserting delta t minus 1 as 0 because we start off with 0 initially. We evaluate this to 200. At each step, we make a comparison with W. We see that 200 does not exceed 550, which is why we do not make a state change. Delta 2 is iteratively in the next iteration calculated as 400. We see that this does not exceed 550, again no state change. Now delta 3, this evaluates to 600, which is greater than 550. Now we know that the state should be switched to SH. Now we reevaluate starting from delta t equal to 0. So our delta 4 is evaluated as 0. Similarly, delta 5, delta 6. And now Delta 7 is evaluated to 200. Delta 8 increases, delta 8 is 400, and delta 9 is 600. We see that this exceeds 550, and so we change the state to SL, and this process repeats. We consider the following performance metrics. For adversarial arrivals, we consider the performance of policy P as a competitive ratio. We take the supremum over all arrival sequences and we compare with the optimal offline policy, the cost of our policy, our proposed policy P. The performance metric sigma is defined as the total expected cost incurred under the optimal online policy versus the total expected cost incurred under policy P. We show that the following bounds on the competitive ratio of BLTN exist. If delta kappa greater than delta C, then we uh, can say that the maximum ratio of the total cost of BLTN and the optimal online policy under all possible arrival sequences is bounded by this number. For a deterministic online policy, we see that the competitive ratio of policy P is a minimum of these three numbers. We also show that a bound exists on sigma BLTN. So considering an arrival process to be IID stochastic, we say that sigma BLTN is bounded by this factor. Here psi decays exponentially with W, which is the sum of switch costs. It also decays exponentially with the difference of expected service and rent costs. It's inversely proportional with the differences in the limits on the number of requests that can be hosted by the edge server. The FTPL policy, follow the perturb leader, is defined as follows. We consider total costs incurred in state H or state L until time slot T for a policy that is static in state H or state L. Now we make a difference in the comparison of the policies and we observe the perturb quantity delta C and we add a Gaussian noise to it and we compare which of the policies incurs a greater cost. We consider a Gilbert-Elliott model as a two-state model where the transition probability is B and each of the arrival sequence is modeled as a two-state model where S0 has a Poisson lambda 0 arrival sequence and state 1 has a Poisson lambda 1 arrival sequence. The transition probabilities are small, roughly in the order of 0.01. Our simulation results take these parameters as the basis and we consider performance over 10,000 time slots. We see that BLTN and optimal online policies perform roughly equivalent. However, FTPL tends to falter in some places. The time average cost can be observed to be uh, extremely good for BLTN versus FTPL. FTPL tends to falter in the beginning because it's a very exploratory policy, whereas BLTN tends to stay put. FTPL and BLTN under Gilbert-Elliott model have a consistent time difference. Total cost difference. These are our inferences. In most of the cases considered, BLTN performs better than FTPL. There is a under static parametric distributions of the arrival sequence, both the policies tend to converge to the same state because they find the state with the least expected cost. However, when there are similar static costs, FTPL policy tends to alternate while BLTN tends to stay put. FTPL alternates a lot in the first few time slots, which is why we see an exceedingly high initial cost. Under the Gilbert-Elliott model, BLTN always performs better owing to its ability to draw from conclusions from history, whereas FTPL does not account for switching costs, and so it is suboptimal. BLTN performs better than FTPL, where the transition probabilities are low. However, BLTN tends to perform poorly when there is a high transition probability. BLTN switches very slowly. Thank you. This is the end of the presentation.